Okay, let's go to page 2 and pick up where we left off. We'll do one more of these solving differential equations, and then we'll talk about today's topic, and we'll go back and do some more practice. I think solving the exponential functions today should be pretty straightforward. I think we should need more practice with this. All right, so page 2, number 5. So we have y prime equals x plus 1 times y, bottom of the page. Zoom in a bit here. So we know that we would like to get two fractions to line up with each other. We know y prime can be rewritten as dy over dx. And we want to hold on to our parentheses. We don't want to distribute. The parentheses help us separate our variables a little bit easier. So let's force that 1 below. And cross product. I see some students do this where they skip this step and they try to move things around. So just be aware that when you cross multiply, you're not going to be expecting everything to be lining up perfectly. So you're going to have some x's and y's mixed together. But I like to do this step because having that dy dx's line up as our anchor variables, I think it's an important first step. And then from there, you can decide, okay, is something out of place? Yeah, try not to do too much at one time. It's my suggestion. Again, it's okay if things are out of place, but we do want our dy and dx's lined up initially. Okay, so we ask ourselves, what's out of place? Do we have full separation of variables? And we don't, right? We have something out of place here. We're not going to move the dy dx, but looks like the y is out of place. So we have to move the y over. Okay, where's the y going to end up if we move it over? So it's going to end up on the left side, but is it going to be in the numerator or the denominator? Denominator, okay. I think sometimes I see students do this where they divide it over and it just feels weird seeing that y in the denominator. So they start putting in the numerator and they make it y dy. I mean, sometimes that is the case, but if you're making your decision based off of what looks right or wrong, rely on your algebraic steps and not just whatever looks strange, because it's okay to have your variable in the denominator. We have rules that can handle 1 over u du, right? This is going to be a natural log rule. Okay. So our first step is to try to get our separation of variables. We want our x's, everything related to x's together, everything related to y's together. So now we have full separation. So we can move on to our integral process. I'm going to pull that dy out in front and make it 1 over y dy, just to make it look more familiar in terms of the rule that we want to use. Actually, now we can drop the parentheses if we wanted to, because we've already had full separation. So I don't want us to think of that as a u substitution on the right side. The x plus 1 are basically independent power rule problems. So you drop the parentheses and all right, so 1 over y dy, this is 1 over u du, this is natural log. Right side, power rule, x becomes x squared over 2. 1 becomes x, and then plus c. Everything is up at the function level. We're done with our calculus, and now the one final step left to do is to try to get that y by itself. So y is stuck inside that natural log. The way we undo natural log is we involve the exponential function base e, because we know exponential function base e and natural log are inverses of each other. They're going to undo each other. So I'm going to raise both sides with e as the base. So now our entire equation is sitting up in the exponent spot. Whatever we do to one side, we're also matching our steps on the right side. We're balancing out our equation. But the advantage of this is that now e and natural log have that inverse relationship that's lined up in a way that's going to allow us to remove them and then get down to just the y that we're looking for. So absolute value of y is equal to. We want to separate that c away from the rest of the expression. We're going to use that exponential property that allows us to do that. So base raised to the exponent is the sum of exponents is equal to the bases separated in terms of multiplication. So I don't need to separate that x away from the x squared. I can leave those alone. This is all variables. I'm just trying to get that c to show me a separated coefficient. Notice we're changing operations here. An addition sign in the exponent is the same as the multiplication at the base level. So make sure that you change that operation there, that you don't make that plus c a plus c here. This turns into a multiplied by e to the c. And we talked about how e to the c is just one big constant. E is a number, c is also a number. This is just one big c. So I can replace that c into that e to the c. I can pull that c out in front. We like to have our coefficient in front of our variable. Okay, we're almost there. We're going to drop the absolute value. The absolute value represents plus or minus values, and then a plus or minus ce to the x squared over 2 plus x. And then we know that c can represent both positive and negative numbers. We'll let that plus or minus kind of absorb into that c. So y is equal to ce to the x squared over 2 plus x. let's go through today's topic, and then we'll come back and do more practice with this. Okay. So go to page 5. We're going to talk about this exponential growth and decay equation. Once we get to our equation, we're not going to do much calculus. We're just going to be solving for a bunch of variables. Let's talk about it here. So direct proportion equation is where y and x are directly related to each other, meaning they're both in the x and the numerator. An indirect proportion equation or inverse proportion equation is where y and x's are inversely related to each other. So one's in the numerator, the other's in the denominator. The k is called the constant of proportionality. It's the numeric value that relates the two variables together. So number one, let's see if we can create an equation based off of the sentence that's provided. It says if the rate of change of y, so that's talking about y prime, rate of change of y, so y prime, varies directly. So varies directly, that means it's going to take on this form. We already have what's produced on the left side, y prime, varies directly. So that's going to be equal to k times with the value of y. So it's going to be times y. So this one will be read as y is directly related to the value of x. And this one is read as the rate of change of y varies directly with the value of y. So y prime equals ky. This is our equation. This is our differential equation. And it says find the general equation. So we're going to solve this differential equation. So let's go through our steps here. Now all these problems are in relation to time. So instead of x, we're going to use t. All right, so we're going to have y and t here. So t will replace our quote unquote x. So y prime is, before we would say dy over dx, but now it's going to be dy over dt. So no longer are we going to be using x here. Anytime there's like a word problem, it's usually time that's pushing the problem forward. So our independent variable, if there's time involved, it's always time and our other dependent variable. Time is our independent variable. Okay, so let's cross multiply. Remember, k is just some numeric value. So treat k like you would like a 5 or 6 or 8. Okay, so cross multiply here. So y dy. Wait, I'm sorry. I did not write my equation correctly. It's back up. My bad. dy over dt equals ky. And we're going to force a 1 below. We're not going to do k over y. Sorry about that. So we're rewriting y prime as dy over dt. We want to force that 1 below our denominator so that we can cross multiply, so that we can have our dy and dt's lined up nicely. Right, so when we do our cross product, we have our dy and dt in their right spots. These are our anchor variables. We always want them in the numerator. We always want them on opposite sides. So now we ask ourselves, what's out of place here? Are all the t's together and all the y's together? Remember, k is not a variable. It's like just a number. So we usually want whatever we don't need on the right side. So the only thing that's out of place is this y. So we're going to move this y over. We're going to divide by y. So if we divide by y, it's going to end up in the denominator. So dy over y. equals k dt. Okay, we can set up our integral now. Everything is nicely separated. Now remember, k is just a number, so we like to put a number outside of our integral, and it's really just the 1 dt that we're taking the antiderivative of. So we're not going to do k squared over 2 because k is not a variable. It's the one that's that we're taking the antiderivative of. Okay, so 1 over y dy, that's natural log. K stays, 1 becomes t, so it's going to be k times t plus c, right? The antiderivative of 1 rises up to degree 1. dt tells us that the variable that we're working on is time, so or variable t. So if it was 1 dx, then 1 will go to x, but it's 1 dt, so 1 goes to t, and then plus c. Right, we want to solve for y, so raise both sides with e as the base. E in natural log goes away nicely. We want to separate that c away from my variable, so I want to drop that plus sign down to multiplication, so it becomes e to the kt times e to the c. I can convert that e to the c to just be one large c in front, and I can drop the absolute value. And the plus or minus gets sucked into the c. So from now on, if you ever see this relationship, whether it's like y prime equals ky or p prime equals kp or b prime equals kb, anytime you have this relationship, you can skip all this and just jump directly to this equation. Okay. We're going to use this a lot. So anytime you see that relationship, you know, okay, this is going to end up, I don't have to go through all this process. I know it's going to end up at this level. And so once we know we're at this level, a lot of times these problems, we're going to skip a lot of the calculus. We're just going to be working on trying to solve for different variables in this equation. All right, so number 2, the rate of increase of population is proportional to the population. So again, we're going to set up a similar differential equation as we did for number 1. The rate of increase of population, that's going to be talking about the derivative of population. So we'll call it p prime. Is proportional. So if you see the word proportional, the understood word is that it's directly proportional. If they don't mention direct, then it's understood direct proportion. If they want inverse proportion, they have to state it. So proportional is just direct proportional to the population. So just like how we have y prime equals ky, here we'll say p prime equals k times p. So basically, this is dp over dt is equal to k times p. And this is going to work it out the same way. It's just that now instead of our variable being y, our variable now is going to be p. So we can just go skip all this and jump to our equation that we're going to be working on. So p is equal to ce to the kt. It's the exact same relationship as above. We're just going to skip all the calculus, and then we'll move on to solving this problem. Right, there's a lot of numbers here because there's a lot of quite a few variables that we're trying to solve for. So I like to organize my data using order pairs. So I like to do this. I like to say, okay, I'm going to create a bunch of order pairs. Time is my independent variable. In this case, population is my dependent variable. So I'm going to organize all my order pairs as kind of my x, y, but is now t comma p. Let's read the problem here. If the population in 1930 was 50,000 and in 1960 was 75,000, what's the expected population in 1990? To make it easier so that we don't have to deal with such large values in terms of year, we're always going to to make it easier for us algebraically, whatever the earliest year that we can recognize, we're going to use t equals 0 for that year. So what's the earliest year that you see? 1930. Okay, so we're going to let 1930 be t equals 0. We'll let 1930 be year 0. So we're going to say year 0, or 1930, the population was 50,000. So I'm going to say year 0, comma, 50,000. In 1960, the population was 75,000. So what order pair can we create here? 30. Yeah, this is 30 years after my initial year. So 30 years later, my population is 75,000. Right. What's the expected population in 1990? How many years after 1930 is this? 60. So we're going to say in year 60, we're going to figure out what is the predicted population. That's the unknown. So we like to take advantage of year 0 because year 0 will wipe out a lot of things that were and allow us to isolate our variables easier. So I'm going to plug 0 in for t and 50,000 in for p and see what that gets me. So 0 in for t and 50,000 in for p. And you will get to use your calculator on your test. So just want to point that out. All right, what's anything raised to the 0 power? Well, k times 0 is 0, right? Okay, and then what's anything raised to 0 power? 1. So that's going to wipe that out to just 1 times c. So c equals 50,000. Okay, so once you find a value for a variable, you're going to update the equation with what you just found. So my updated equation now is p is equal to 50,000 e to the kt. Okay, so the first order pair is useful in helping us solve for c. Now let's move on to the second order pair. So again, same process, but now with an updated equation. 30 in for t and 75,000 in for p. All right, we want to solve for k. K is stuck in the exponent. I want to kind of move things away from that right side there. So an easy thing to move first is dividing by 50,000. So I'm going to divide by 50,000 first. $75,000 divided by 50,000 gives me 1.5. So I get 1.5 is equal to e to the 30k. All right, so we have an easier equation, but we're still trying to solve for k. K is stuck in the exponent. We would like to bring the exponent down, but we can't just bring it down and not change the problem. So what can we introduce into our equation so that our exponent can be free to move? Natural log. So let's introduce natural log into our equation, and that will allow our exponent to freely move in front. Now the 30k can come down. One thing we know about natural log of e is just going to be 1, so that's going to go away. So we're left with natural log of 1.5 equals 30k. Now we can solve for k, divide both sides by 30. So k is equal to natural log of 1.5 divided by 30. Now, we're not at the end yet. So even though you could grab a decimal out of this. If you get a decimal at this stage, it's going to decrease the accuracy of your end solution. So we want to hold on to this mess so that we can get a more accurate solution. When we get to our very end decimal value, we can round to 3 decimal places. But for now, let's hold on to this value. Okay. So I'm going to update this. K is equal to natural log of 1.5 divided by 30. Okay, so now that we have our K value, we're going to update our equation again. We have our C value replaced with 50,000. Now we're going to replace the K with a numeric value as well. So it's going to look a little messy, but just have to write it out because the calculator can do all the numeric stuff for us. 50,000 e to the natural log of 1.5 over 30 times t. So P is equal to C e to the KT. We've replaced 50,000 because of this order pair. We've replaced the K value with natural log 1.5 over 30 because of the second order pair. And now the third, now we have enough information to plug in 60 in for T and then plug all this in and then solve for P. Right. We had 3 missing variables, but now we've resolved 2 of them. And now we can plug 60 in for T and solve for P. So P is equal to 50,000 e to the natural log of 1.5 over 30 times 60. Okay, so practice entering that in your calculator. See what you get. It just so works out that ends up not having a decimal, but usually there's going to be a decimal. If there's a decimal, you're going to round to 3 decimal places. So the population is 112,500. In 1990. All right, number 3. Does anybody still need this? So number 3, you're going to set up most everything the same way. So it says the rate of decay is proportional to the amount of radium present. So R prime is equal to K times R. It'll work itself the same way. It's like Y prime equals KY. It's like P prime equals KP. So you can just jump directly through the equation. R is equal to CE to the, I'll use lowercase. So we're going to create a bunch of order pairs like we did with this problem. But instead of time and population, we'll do time, comma, radium. So if 60 milligrams of radium are present now, and its half-life is 1,690 years, how much radium will be present 100 years from now? So present day is going to be year 0. So current day, we have 60 milligrams of radium. Half-life, so we know 1,690 years from now, the radium is going to decrease to what? The amount is going to decrease to what? 30, half-life. So 30 milligrams will remain. So it'll take that long for that amount to decrease by half. So how much radium will be present 100 years from now? So 100 comma radium. So we'll plug 060, solve for C, update it, plug in the second order pair, and for T and R, and we can solve for K. And once we have C and K figured out, then we can plug in 100 in for T and solve for R. Take the natural log of both sides to allow that exponent to come down so that we can solve for K. Okay. Update your radium equation. You have your C value figured out. You have your K value figured out, but don't do a decimal for K. Hold on to this mess of a value. This is an exact value which will help us get the most accurate approximation at the very end of the problem. So now we're ready to plug in 100 in for T. Make the calculator find our radium amount. Okay, number 4 is a little bit different because normally we know the initial amount and then we solve for k, and then we solve for k and then we try to figure out a predicted value. Now it's going to be a little bit different where we have a specific random order pair and we have something to help us solve for k, but then we're trying to look for our initial amount. We're working backwards, but we're still going to create our initial list of order pairs here. So number 4, in a certain bacteria culture where the rate of growth of bacteria is proportional to the amount present. So the same relationship, B prime is equal to K times B. So B is equal to CE to the KT. All right, so again, time is always our independent variable. So it's going to be time t followed by the amount of bacteria. So T for time and B for bacteria. So we know that there is some initial amount. So we're going to say if at the end of 12 hours there's 10 million bacteria, how many were present initially? So initially means time 0. How much bacteria is in at time 0? So I'm going to say time 0. We have some unknown, and typically now that we're seeing it, that a lot of these values, these numbers end up being our C value, right? Our C value is the number that we see here is the C value at time 0. So I don't know what C is, so I'm going to say 0 comma C. It's some initial amount that I don't know yet. But I do know that the number will triple in 3 hours. So that means 3 hours later, what's going to happen to my C value? The number will triple, so what can I do with C? What's triple the value of C? Well, how can I represent that? 3C. Right, triple my initial amount. Right. Again, I don't know what it is, but I have that relationship based off of what they say here. If at the end of 12 hours there's 10 million bacteria, so 12 hours later, I could write out 10 million, but I'm just going to say comma 10. And in the end, at the end of my problem, I just remember to multiply my answer by 1,000,000 because I'm representing an easier number in terms of 1,000,000 so that I don't have to deal with such a big number in my calculator. So at the very end, just make sure we multiply our answer by 1,000,000. 10 represents 10 million for now. Okay, so our equation, B is equal to CE to the KT. 0C is not going to make us, it's not going to make any progress for us, right? So we can ignore this. Eventually, we will solve for this, but we can plug this in. 3 in for T, 3C in for B. Do we see anything that we can do to reduce this equation? What can we do to make this equation simpler here? What can we remove? Yeah, I can divide both sides by C and allow myself to just focus on solving for K. Natural log of both sides. Bring the 3K down. You know, natural log of E is equal to 1. That goes away. divide both sides by 3, so natural log of 3 over 3. Update our bacteria equation. Now we should be able to solve for C, 12 in for time, 10 in for B, and then we should be able to make our way to solve for C, and that will tell us how much bacteria there is to begin with, given these other order pairs. Okay, I'll divide both sides by e to the 4 natural log of 3, and that should allow me to isolate C. And remember, we have to multiply by 1,000,000 since we're using an easier number for our calculator here. I got 0.1234567, so multiply that by 1,000,000. So 123,456. Okay, the most important topic of this unit is solving differential equations. So I'd like for us to get a little bit more practice with that. We'll get a ton more practice next week, but let's turn to page. I have a lot of practice problems later on in this packet here. So turn to page 16. Let's try our separation of variables practice steps again. Okay, page 16. Y prime equal minus xy cosine of x squared is equal to 0. So we're going to start off by try to separate our, well, let's get the two terms on opposite sides of the equation first. And then we can go through all of our steps. All right, start off y prime. Let's rewrite as dy dx. Let's get our denominator to show a 1 so we can line up our diagonals. Okay, cross multiply. When you cross multiply, your dy dx's will be lined up nicely. But that's our first step. Doesn't mean that we're ready for our integral, but it's nice to have our first step give us that progress there. Next step, do we have full separation of variables? We can't take the integral until we have full separation. Do you see something out of place? The y. So what do we do? Divide it. Where's it going to end up? Denominator. Good. So that should be the only thing, right? Divide by y. So 1 over y dy is how my left side will look. And my right side will be integral of x cosine x squared dx. Everybody comfortable with all these steps leading up to our right before our integral? Okay, so cross multiply, move variables if needed. Y is on the left, X is on the right. Now we can move on to our integral step. The left side is pretty straightforward. That's just natural log. But the right side, we got to go through a little bit of what? U substitution. What's our U value? X squared. Good. All right. So let's go through our steps. Having to basically work on both sides of the equation separately here. Dx equals du over 2x. That should be pretty nice to help us line up our x's there to cancel out. Let's see. X cosine of u times du over 2x. There is a 1/2 left over. We know the integral of cosine is a positive sign, so we can do that. And then replace the u back in terms of x. And the left side, it's just going to give us natural log absolute value of y. And then plus c. Okay, so we're not done yet, but we're done with the calculus. We've taken care of all the integral here. Now the remaining portion of the problem is to solve for y, and then the order pair that's given to us to solve for c. So any questions up to this point? Okay. All right, so let me reset at the top of the page here. And then we can move into doing some cleanup. Now, at this stage, you can either solve for y or solve for c. It doesn't matter. There's really no rhyme or reason in terms of, sometimes I feel like I want to solve for c earlier because it feels like an easier equation. But ultimately, you got to solve for c, you got to solve for y. So you may do things in a different order than me. And also, if you do things in a different order than me, you may get a different c value, but it doesn't mean that it's wrong. It just means that you're solving for c at a different point than me. But in the end, if we agree at the end, then that's fine. Okay, so don't worry about, oh, wait, my c doesn't look like your c value. So typically, when I see natural log, I find it a little bit easier to just solve for c. It's just a little bit messy to solve for. Sorry, I like to solve for y because natural log feels a little messy to me. So I like to get rid of natural log earlier the better. So erase both sides. E as the base. E and natural log goes away. I'm going to separate my variable away from my constant. We know that, remember, your plus in the exponent is going to turn into a multiplication at the base level. We can drag the c out in front. And then drop the absolute value because we know the c will absorb the plus or minus. So I have my general equation. They give me an order pair, and I can now update my general to a specific or particular. So I'm going to plug in my order pair 0, comma e. 0 in for x, e in for y. The nice thing about that 0 is going to wipe out this entire exponent. E to the 0 is just going to be what? 1. So my c is just equal to e. So now we just have to update our equation and replace c with e, and we're done. Or you could also do this. You can make that e to the first power, and then you can merge it and say y is equal to e to the 1 plus 1/2 sine x squared. Now, most of us are not going to want to take this this final step. I just want to point this out to you because on the AP exam, if it's multiple choice, they may take this answer and go one step further and write it in this form. Okay, we're gonna pick up next week with either notes or review, but no homework this weekend. We'll pick back up on Wednesday. Okay. All right, come get your phones. Hey.
Showing my homework.
Okay.
Last week. I had 5 and 6.
Yeah.
Homework packet.
Yes. I think page 11. Well,
I like them. I mean, it's not gonna look like a podcast, like voice back. No, that. It has like it won't be sense.
yeah,
Right?
it was this packet, the first review.
Oh, yeah.
Off of the unit.
I still like that. Wait, I swear I had it. Show it to you when I find
That's fine. That's fine. Yeah, it's just whenever. This is what we did right before. Okay.
Oh wait, I think this is.
Okay. Okay.
I just didn't put my name on.
I see. Okay. Good. Thank you.